Here's a physics puzzle that looks simple at first glance, but it tricks a surprising number of people. Take a careful look at these two tanks. Tank A is placed on a lower platform. Tank B is placed much higher above the ground. Both tanks are identical in shape. Both contain the same amount of water. And both have exactly the same outlet opening near the bottom. Now before we continue, I want you to make a prediction. Which tank do you think will empty first? Will it be tank A? Will it be tank B? Or will they somehow empty at the same time? Pause for a moment and decide your answer before we begin. Most people are very confident about their choice. Let's see if that confidence survives the experiment. If you chose tank B, you're not alone. In fact, that is the answer most people give. The reasoning sounds perfectly logical. Tank B is higher. Gravity pulls everything downward, so it feels natural to assume that the water in tank B should rush out faster. After all, if you drop an object from a greater height, it gains more speed before reaching the ground. Many people apply the same intuition here. A higher tank should mean faster drainage. At least that's what our intuition tells us. But physics is full of situations where intuition can be misleading. So instead of arguing about it, let's perform the experiment and watch what actually happens. We now open both outlets at exactly the same moment. Watch the water levels carefully. Notice that water begins flowing from both tanks. At first glance, everything looks normal. Tank B is still much higher above the ground. So if height alone were the deciding factor, this would be the moment where tank B starts pulling ahead. Keep watching. Compare the water levels. Neither tank seems to be gaining an advantage. They continue draining side by side. The levels fall together, and something very surprising is about to happen. And there it is. Both tanks finish draining at exactly the same time. Not almost the same time. Not close. The same time. Even though one tank was placed significantly higher than the other. This result surprises many people because it directly contradicts what they expected. So now we have a much more interesting question. Why doesn't the extra height help tank B drain faster? Where did our reasoning go wrong? To answer that, we need to understand what actually controls the speed of water leaving a tank. The key idea is that the ground does not matter. Let me say that again. The distance between the tank and the ground has absolutely no effect on how quickly water leaves the outlet. What matters is something completely different. The only important height is the vertical distance between the water surface and the outlet hole. Physicists usually call this height h. As long as that height is the same, the pressure pushing water out of the hole is the same. And if the pressure is the same, the water exits at the same speed. Notice that both tanks started with the same water depth above their outlets. That means both tanks started with exactly the same pressure at the hole. So the water in both tanks leaves at exactly the same speed. Since the tanks are identical and the flow rate is identical, they require the same amount of time to empty. The platform underneath the tank changes the position of the tank relative to the ground. But it does not change the depth of water above the outlet. And because that depth stays the same, the drainage behavior stays the same. This result can be described mathematically using Torricelli's law. According to this law, the speed of water leaving an opening is proportional to the square root of 2 times gravitational acceleration times the height of water above the opening. The important thing to notice is that the equation contains the water height above the outlet. It does not contain the height of the entire tank above the ground. The ground never appears in the equation. And that's the reason our intuition fails. We tend to focus on the overall height of the tank. Nature focuses only on the height of water above the outlet. So the next time someone tells you that the higher tank must empty first, remember this experiment. The height of the platform does not determine the drainage speed. The height of the water above the outlet does. That's why these two tanks, despite being at different elevations, empty at exactly the same time. Physics often challenges our instincts. And that's what makes it so fascinating. Did you predict the correct answer? Let me know in the comments. And if you enjoy visual physics puzzles like this one, stay tuned for more. In our last video, we proved that elevation alone doesn't speed up how fast an open tank drains. This leaves many people confused. If elevation doesn't help a tank empty faster, why do municipal cities and engineers build massive water towers high above the ground? And what happens to our physics puzzle if we attach enclosed vertical pipes extending down from both tanks to the ground? Does tank B finally drain faster? Or do they still empty together? Let's explore the physics when enclosed plumbing enters the equation. First, let's answer why water towers are elevated in real life. When you want to deliver water to modern homes through underground pipe networks, you need pressure. The hydrostatic pressure inside an enclosed vertical pipe is calculated by density times gravitational acceleration times total height h. Every extra meter of height drop adds static fluid pressure at the base of the pipe. This elevation pressure overcomes internal pipe friction, negotiates sharp pipe bends, and pushes water up into multi-story residential buildings without requiring continuously running electrical pumps. So water towers are elevated to create pressure inside a closed network, not to empty the tower itself faster. Now let's return to our experiment, but this time with a crucial modification. We attach sealed vertical downspout pipes to the outlet holes of both tanks, extending all the way down to ground level. Tank A has a short pipe. Tank B has a much longer pipe because it sits higher up. Before we open the valves at the bottom of these pipes, make your prediction. Will both tanks still empty at the same time? Or does adding vertical pipes completely change the outcome? Let's open both valves and watch what happens. We open both valves simultaneously. Look closely at the water levels now. Tank B's water level is dropping noticeably faster than Tank A. By the time Tank B is completely empty, Tank A still has a significant amount of water left inside. With vertical pipes attached, Tank B empties first. Why did adding pipes completely reverse the previous result? To understand why, we turn to Bernoulli's equation for fluid dynamics. Bernoulli's principle states that the total energy in a steadily flowing fluid system remains constant along any streamline. Without a pipe, water exits into open air right at the tank base. So the driving height is only the internal water depth h. But when an enclosed pipe is filled with water, the fluid column forms a continuous seal from the top surface all the way down to the pipe exit at the ground. This means the total vertical drop h pipe now contributes directly to the exit velocity equation. The exit velocity becomes the square root of 2 times g times the sum of the internal water depth plus the pipe height. Physically, gravity pulls downward on the heavy column of liquid hanging inside the vertical pipe. This downward gravitational weight creates a low pressure area, effectively a vacuum suction effect, at the outlet hole of the tank. Because tank B has a much longer vertical pipe, the weight of the water inside its pipe is greater. This creates a much stronger negative pressure that actively sucks water out of tank B at a much higher flow rate. In summary, if water exits directly into the open air from a hole in the tank, elevation does not matter. Both tanks empty at the exact same time. However, if water flows through an enclosed vertical pipe extending to the ground, The extra height creates a siphon effect that pulls water out faster. Understanding the boundary conditions of fluid mechanics is what separates intuition from true physical insight. If you found this mathematical breakdown helpful, like the video and subscribe for part 3, where we investigate what happens at extreme altitudes of 500 meters or more. Welcome to part 3. To wrap up our exploration, we need to answer one crucial question. Does altitude above sea level change how fast a tank empties? The secret to understanding this comes down to two completely different meanings of the word height. Let's compare case 1, where a tank sits on a mountain, versus case 2, where a pipe runs all the way down the mountain. In case 1, consider tank A at sea level and tank B on a mountain 500 meters high. Both tanks are open to the air, contain 2 meters of water depth, and drain right beside their bases. The exit velocity equation is V equals the square root of 2 grams h, where h is only the water depth above the hole. Atmospheric pressure acts on both the open top surface and the outlet hole, cancelling out completely. Plugging in a 2-meter depth yields an exit speed of 6.26 meters per second for both tanks. Water does not care how high the mountain is above sea level. Moving the tank to a mountain is like being inside an elevator. Raising the entire system 500 meters creates zero new pressure differences within a system. Now consider case 2. Suppose we connect tank B on the mountain to an outlet all the way down at sea level using a long pipeline. Now the elevation drop is 500 meters. The total driving head H is no longer just 2 meters of water depth. It is 500 meters of potential energy. Using the equation versus equals square root of 2 grams h, the exit velocity rockets to roughly 99 meters per second. Now the mountain matters enormously. This massive elevation drop is precisely how hydroelectric power plants generate energy from mountain reservoirs. Here is the entire physics lesson in one simple sentence. Altitude above sea level does not matter. The height difference between the water surface and the outlet does matter. When the outlet is attached right beside the tank, the driving height is just the water depth. When the outlet extends down a mountain pipe, the driving height is the total drop. Thank you for watching this 3-part series. Let me know in the comments what physics concept we should break down next. Welcome to part 4, our bonus episode for ultra-precise physics enthusiasts. In part 3, we stated that altitude above sea level does not change how fast an open tank empties. A sharp viewer might object and ask, doesn't gravitational acceleration g decrease as you move farther away from Earth's center? If g drops at 500 meters altitude, shouldn't tank B drain slightly slower than tank A? The short answer is yes, technically it does. Let's calculate the exact math to see how big this effect actually is. Gravitational acceleration at height h is calculated using the inverse square law, where r is Earth's radius of roughly 6,371 meters, 6,371 kilometers. At sea level, standard gravity G0 is approximately 9.80665 meters per second squared. Plugging in altitude of 500 meters into the equation gives a high altitude gravity of 9.80510 meters per second squared. That is a tiny difference of just 0.015%. Now let's plug these exact gravity values back into Torricelli's exit velocity formula for our 2-meter water tank. At sea level, the exit speed is 6.2631 meters per second. At 500 meters altitude, the exit speed drops to 6.2626 meters per second. The theoretical difference is roughly 0.5 millimeters per second. In a physical experiment, this millimeter per second shift is completely drowned out by water surface ripples, air currents, and thermal expansion. So, is the statement, altitude does not matter, wrong? In engineering and introductory physics, when we say altitude doesn't matter, we mean that elevating a tank creates zero additional hydraulic pressure head. While the minuscule variation in G is real, it is far too tiny to matter in practice. Understanding when minor physical effects can be safely simplified is part of thinking like a true physicist. Thanks for watching this 4-part deep dive. Subscribe for more visual physics puzzles.